So at this point we're going to assume that you're happy with the electrophilic addition mechanism for alkenes and that you're now ready to take on the extra complications when you have an unsymmetrical alkene and an unsymmetrical reagent adding across the double bond. So let's take as our example propene, where the two carbons with the double bond are not the same, they have different groups, so it's not symmetrical on either side, and we'll take HBr as a reagent that's going to be adding across the double bond. So we have two possible products here depending on which way it's lined up and which way it adds across. So we can take, for example, the double bond here breaking, the hydrogen joining on here and the bromine joining on here, of course meaning this bond disappears. Or we could have it as in this molecule where the bromine adds here and the hydrogen adds here, giving two different products. In this case we have one bromopropane where the bromine is on the first carbon in the chain, and in this case here we have two bromopropane where the bromine is on the second carbon on the. So to help us get the right product we have the Markovnikov rule, and basically what this says is the hydrogen will attach to the carbon that has the most hydrogens already attached. Or in other words, in terms of hydrogen, the rich get richer. This is to help you remember, but it's not the reason it happens. It's not an explanation of why. So if we flash back to the last page, we'll see that this is the product we'll get because our hydrogen is added onto that carbon that already had two, whereas with this one, the hydrogen added onto the hydrogen that only had one hydrogen already attached to it. And of course, to explain that now, we need to look at the actual mechanism of the electrophilic addition. So here we have our hydrogen bromide and our alkene, and the polarization delta positive for the hydrogen, delta negative for the bromine. So as it approaches, this bond breaks to make a bond with the hydrogen, causing this bond to break and the electrons to move to the bromine. This gives us the carbocation intermediate, and this is the focus of our explanation. So this positive charge making our carbocation, we see is on a carbon that's attached to two other carbons. That makes it a secondary carbocation. To make the other product, we would have to form a primary carbocation, which is not so stable. And now, having formed our carbocation and our bromide ion, this will then attach on there as per normal to finish off and give us our final product. So let me show you what I mean if we were to get the other product, which we don't by this mechanism. So here we've lined the bromine up the other way, and in order for the hydrogen to go on this middle carbon, this would form the bond here and this bond would break, leaving us with this carbocation intermediate. where the positive charge is now on this carbon here. Now we see that this carbon is attached to only one other carbon, making it a primary carbocation. This is less stable than a secondary one and is therefore less likely to form. So under normal conditions we don't get this. Let me stress, this is not normal. So normal laboratory conditions will not give us this, will give us the secondary carbocation. So the reason for Markovnikov addition, the Markovnikov rule, has to do with the relative stability of carbocation intermediates as they are formed. And these are quite important because a tertiary one where the positive charge is on a carbon attached to three others is more stable than a secondary one, and therefore will form preferentially. And a secondary one, as we already discussed, is more stable than a primary one. This is a reason why Markovnikov products are produced. So under normal conditions. And there is a but. Something that we should be aware of is the reaction conditions, because we can get the alternative product but by a different mechanism, and that would be free radical. And we tend to call that the anti-Markovnikov product. So it's the other one. And we recognise the free radical by checking out the conditions. It's going to either say H mu or ultraviolet light, or maybe even peroxide. So basically what you need to watch out for is the conditions. If it says normal, it's Markovnikov. If it's a free radical, H mu, UV light, peroxide, then we're looking for the alternative product, the anti-Markovnikov. So check the conditions.